What specific problem does MIO aim to solve in the context of multimodal learning, and how does it address the limitations of existing MLLMs?
MIO, Multimodal Input and Output, aims to solve the limitations of existing multimodal language models, MLLMs, by unifying multimodal understanding and generation across four modalities: text, image, speech, and video, while enabling the generation of multimodal interleaved sequences. Existing MLLMs often focus on dual modal capabilities, primarily combining text with one other modality, and neglect the generation aspect, leading to limited multimodal instruction following and reasoning capabilities. MIO addresses these issues by employing a discrete multimodal tokenization approach that captures both semantic representations and low-level features, allowing it to treat non-textual modalities as foreign languages and utilize a next-token prediction paradigm for training. Additionally, MIO's three-stage pre-training process enhances its performance across modalities, ensuring that it can effectively generate and understand multimodal data, including interleaved video text generation and chain-of-visual thought reasoning. This comprehensive approach positions MIO as a competitive alternative to existing models, demonstrating superior capabilities in both understanding and generating multimodal content.
Can you explain in detail how the proposed MIO method works? Please illustrate it step by step, including aspects like tokenization, modeling, and detokenization.
The proposed MIO, Multimodal Input and Output method, operates through a structured framework that encompasses three main components: tokenization, modeling, and detokenization. 1. Tokenization. MIO employs specialized tokenizers for different modalities. For images, the seed tokenizer encodes images into discrete tokens using a bit derived from BLIP2, resulting in 32 tokens per image. For speech, the speech tokenizer generates 400 tokens per second by separating content and timbre tokens, with a total vocabulary size of 4096. Videos are tokenized by converting them into image sequences, where each frame is treated similarly to an image. 2. Modeling. The core of MIO's modeling involves causal multimodal modeling, where the tokenized inputs from various modalities are integrated into a unified model. The model extends the LLM's vocabulary to accommodate the new multimodal tokens, allowing for next-token prediction training. This enables the model to understand and generate multimodal data simultaneously, leveraging causal semantics inherent in the tokenized representations. 3. Detokenization. After generating multimodal tokens, MIO utilizes modality-specific decoders to reconstruct the original modalities. For images, the seed tokenizer's decoder is used to convert tokens back into images via a diffusion model. For speech, the model generates timbre tokens autoregressively, which are then synthesized into speech using the speech tokenizer's decoder. Overall, MIO's architecture allows for seamless integration of multimodal understanding and generation, enabling it to produce interleaved sequences across text, images, speech, and video.
Could you provide a simple illustrative example demonstrating the inner workings of the MIO algorithm, specifically focusing on how it handles a multimodal input-output scenario?
The MIO algorithm operates by utilizing a unified framework for multimodal input and output, allowing it to process and generate data across four modalities: text, image, speech, and video. For instance, consider a scenario where the model receives a video input, along with a text prompt asking for a summary. The video is first tokenized into image sequences using the seed tokenizer, while the text is processed through the language model. The model then employs causal multimodal modeling to understand the context of both the video frames and the text, generating a coherent summary that interleaves both modalities. This output can include a combination of generated text and visual elements, demonstrating MIO's capability to produce multimodal interleaved sequences. The entire process is facilitated by the model's three-stage pre-training, which ensures that it effectively learns to align and generate across these diverse modalities.
What are the practical benefits of using MIO compared to existing multimodal models? Can you quantify any improvements in efficiency, accuracy, or capabilities?
The practical benefits of using MIO, multimodal input and output, compared to existing multimodal models include its ability to unify multimodal understanding and generation across 4 modalities: text, image, speech, and video, while enabling the generation of multimodal interleaved sequences. MIO demonstrates competitive performance in various tasks, outperforming several larger models, such as MU14B and IDE-FICS80B, despite having approximately 7 billion parameters. Specifically, MIO achieves high scores in image understanding tasks, ranking among the top models, and exhibits strong capabilities in speech understanding and generation, surpassing the any GPT baseline. Additionally, MIO's innovative 3-stage pre-training process enhances its efficiency in training across modalities, allowing for better optimization of speech capabilities without compromising performance in non-speech modalities. Overall, MIO's design leads to improved multimodal instruction following, reasoning, and the ability to generate context-aware images, showcasing its advanced capabilities over existing models.
How did you validate the performance of MIO? Describe the experimental design, datasets used, and the metrics employed to assess its effectiveness across different modalities.
The performance of MIO was validated through a comprehensive experimental design that included quantitative evaluations across various domains: image-related tasks, speech-related tasks, and video-related tasks. For image understanding, MIO was compared against models like EMU, SeedLlama, and any GPT using benchmarks such as the MS-CoCo-Carpathy test split for image captioning and visual question answering metrics like VQA accuracy. In speech-related tasks, MIO's performance was assessed on automatic speech recognition (ASR) and text-to-speech (TTS) tasks, utilizing datasets like LibreSpeech and comparing against baselines such as Wave to Vec2, 0 and Whisper Large V2. For video-related tasks, MIO was evaluated on MSVDQA and MSRVTTQA, achieving the highest scores compared to other models. The metrics employed included CIDR scores for image captioning, word error rate (WER) for ASR, and qualitative demonstrations for emergent abilities, showcasing MIO's competitive performance across all modalities.
What were the key results obtained with MIO in terms of performance benchmarks against other models in image, speech, and video tasks?
MIO demonstrated competitive performance in various benchmarks across image, speech, and video tasks. In image understanding, MIO Instruct ranked among the top models, achieving high scores in tasks such as image captioning and visual question answering, outperforming several larger models like MU14B and IDE-FICS80B. For image generation, MIO exhibited strong capabilities, successfully generating visual stories and sequences, and performed competitively on benchmarks like MS-CoCo and Flickr 30K. In speech tasks, MIO's performance on automatic speech recognition (ASR) and text-to-speech (TTS) tasks was comparable to specialized baselines, outperforming any GPT, particularly in generating both content and timbre tokens. Lastly, in video-related tasks, MIO achieved the highest scores on benchmarks like MSVDQA and MSRVTTQA, showcasing superior performance in both video understanding and generation.